Hello, this is Team BCG, the Bank Consulting Group. Our team is comprised of Anand Patel, Robert Bulowski, Cal Pierce, and Harsha Agarwal. Our project topic of an engineering failure was the Hubble telescope's spherical aberration. Here is the outline of the presentation. Our team consists of upperclassmen computer and electrical engineers. We have interests within the defense and aerospace industry. Therefore, it was easy for us to pick a topic such as the Hubble telescope to discuss. In regards to the engineering failure for discussion, immediately after the launch of the Hubble telescope, the images received from NASA were received as blurry images. This was caused by spherical aberration. What does spherical aberration mean? Well, it means the wrong shape of the mirror causes light to focus in a different area than predicted by the engineers and scientists.
This is Rob Bulowski. I'm going to cover the quick facts and timeline of the Hubble Space Telescope project. It was named after Edwin Hubble, who discovered the universe was expanding in 1925. The telescope was a joint effort between NASA and the European Space Agency, with the ESA being guaranteed 15% of the telescope's research. Lockheed was the main contractor for the spacecraft and overall project, while Perkins-Elmer was contracted to build the optics and subsequently failed to build the main mirror properly. It's significant to note that the error was actually detected twice and ignored. Kodak and iTech initially lost the bid to make the main mirror and then had their backup mirrors canceled because of delays in budget. It was also found later on that Kodak's process would have made the mirror correctly, or at least caught the error. Hubble's dimensions, budget, and life cycle are huge. It took decades to take Hubble from concept to reality. Once funding was approved in 1977, it took 3 years just to make the main mirror, which was severely delayed and way over budget. The entire project was delayed about 7 years total, mostly due to the Challenger explosion in 1986, which delayed shuttle missions for years. Once launched in 1990, it took a couple months to realize that the mirror and imaging were flawed. It took another 3 years and around $100 million to fix it in 1993, with the deployment of CoStar on board the Space Shuttle Endeavour.
The solution that NASA and Ball Aerospace came up with was CoStar. That stands for Corrective Optics Space Telescope Axial Replacement. It was a set of small mirrors that would intercept reflecting light from the mirror and in turn correcting the flaw. NASA hired Ball Aerospace as contractors for this solution. CoStar would work with existing scientific instruments in mind on the Hubble telescope to correct the spherical aberration. For CoStar, the solution would follow the system engineering process. The steps are as follows: needing requirement, system feasibility, system operational requirements, maintenance and support concept, TPMs, functional analysis, requirements allocation, system synthesis, analysis and design optimization, design integration, validation, construction, system operational use and lifecycle support, and lastly, system retirement and material disposal. There's going to be an emphasis in our presentation on a few steps. Those are the needed requirement, system feasibility, system operational requirements, maintenance and support concept, the TPMs, functional analysis, system synthesis, analysis and design optimization, and scrolling down, lifecycle support and system retirement and material disposal, to keep the presentation under the time limit. The first step within the system engineering process is need and requirements. The second step is system feasibility. The problem was identified, as previously stated, as spherical aberration. This was caused by the Perkin-Elmer's Danbury unit. It was immediately decided by NASA and Ball Aerospace to build CoStar as a solution. There were a few options for feasibility, such as creating a new generation of the camera or replacing the high-speed photometer with CoStar. Eventually, CoStar was decided after feasibility studies to be more effective. The next step we're going to discuss is called system operational requirements. The main items to investigate within the Hubble telescope were the number of dependencies of the scientific instruments. These include the faint object camera, which was an optical and ultraviolet camera which was able to count the individual rays of light or light particles as they arrive. The faint object spectrograph, which spreads out light gathered by a telescope so that it can be analyzed to determine such properties of celestial objects such as chemical composition and abundances, temperature, radial velocity, rotational velocity, and magnetic fields. And lastly, the Goddard high-resolution spectrograph, which contrasts with the faint object spectrograph in that it concentrated entirely on UV spectroscopy and traded the extremely faint objects for the ability to analyze fine spectral detail. Other requirements to consider will be environmental factors. COSTAR would have to withstand multiple conditions. First, it would be the impact of launch, approaching orbit, and then space's cold and isolated conditions. The next step to discuss within the system engineering process is a mix of system synthesis, analysis, and design optimization. When talking about system design, engineers should factor in art and science, affordability, requirement fulfillment, and technology integration. Given that the Hubble telescope would be in orbit during its active period, the art aspect wouldn't be taken too much into consideration. Although when integrating design for COSTAR, it's essential that the system assembles correctly and without error within the telescope. After all, the purpose of COSTAR was to correct the spherical aberration caused by the faint object camera, the faint object spectrograph, and the Goddard high-resolution spectrograph.
The next step within the systems engineering process would be maintenance and support concepts. At this point, the primary solution for the spherical aberration from the Hubble telescope proved to be the corrective optics space telescope axial replacement, also known as COSTAR. The contractors for the COSTAR were Ball Aerospace. They are American manufacturers for the space and defense industry, specializing in spacecraft, components, and scientific instruments. The team that constructed the COSTAR consisted of the project engineer, project scientist, instrument manager, and their subordinates. Therefore, they would be responsible for any new issues that haven't been addressed before. This addresses one of the primary teams responsible for conducting off-site maintenance. As for on-site maintenance, it would be conducted in space during the active orbit of the Hubble telescope. The ones who would be responsible for this maintenance would be the NASA astronauts who are trained with proper decor in space maintenance. The retirement process is not simple but straightforward. COSTAR was removed from the Hubble telescope in 2009 during the 5th servicing mission and replaced by the Cosmic Origin spectrograph. It is now on exhibit in the Smithsonian's National Air and Space Museum.